All right, translations. 4.1. So I mean, it's a pretty simple concept, yeah. So I think that's kind of the beauty of it, because a lot of these things, they're all meant to be very simple concepts. They're meant to be simple enough that you can sort of know everything there is to know about them, but non-trivial enough that you can build up long solutions, right? So translations. What is a translation? So you have like A and B, right? And you kind of want to translate them somewhere else. And you kind of want to slide them along, yeah. You get B prime and A prime, yeah. And there's kind of two cases. It can either end up, so these are the same length and parallel, yeah. So it can either end up as a parallelogram, yeah, or it could be translated this way, right, and end up on a straight line, and maybe like a degenerate parallelogram. So it could end up like that, right? Yeah, we like degenerate stuff, don't we?
Yeah.
Okay, so it could stay on the same line, or it could go make it into a parallelogram. And you get translations, okay? So one way to describe this is, so if you think of them as vectors, okay? Have we done vectors? So you can think of this A prime as a vector, okay? And B prime is obviously then the same vector, yeah? So what a vector is, I guess, it's like a geometric, talking about arrows basically, right? You identify all the arrows that are equal length and parallel as the same vector, yeah?
Yeah.
That's what it means to be a geometric vector. And then you can kind of add them head to tail and stuff like that, right? Algebraically, what it means for something to be a vector is it basically means you can add them and you can scale them, okay? So can you see scaling is extending in the same direction, adding them is changing directions, right? And every vector can be identified with the one that the what do you call the vector that goes from the origin? Not the unit vector, but it's like some kind of. You can always shift it so that the tail is at the origin, yeah, and then the head is identified with the point, yeah. But yeah. Anyway, so you can characterize translation entirely in terms of by basically you take your point and you add this vector, yeah,
Yeah.
and then so I guess the identity is a transformation where the vector is zero. So that's the only special vector, right? Because all vectors except for zero have a length and a direction. Zero only has a length and no direction, yeah. So you can characterize translation by sort of thinking of everything as vectors and adding the same vector to everything. Yeah? Okay. So I guess, is it clear then it's an isometry? Yeah? Because it's a parallelogram, right? Or it's on the same line. Okay, so here's an interesting exercise. Wait, I'll show you this one thing before we do the exercise. So, okay, so preserve shape and size of any figure. So the example they gave was this one. So if you have a parallelogram, A, B, C, D, yeah? If you write this 90 degrees here, and this 90 degrees, yeah? This proves that the area is base times height. It's like the height, yeah? So I guess you can sort of see this in two ways, right? but they might actually be equivalent. So if you take this triangle, right, and you translate it, yeah, then you get this triangle, right? So then the area of the parallelogram is just the same as the area of the rectangle. Okay? So you might want to show that, for example, these two triangles are congruent. Okay? And then so the areas are the same. Okay? But actually, like, showing that they're congruent, in other words, is that it comes from an isometry. So showing that the translation gives you that triangle is actually showing that they're congruent, right? So it actually suffices just to show a translation would take this point to here, this point to here, right? And that point to there. After that, like it sends lines to lines and stuff and preserves the distance, because then you get a congruent triangle, right? Or you could show directly the triangles are congruent, okay? And then realize that that must have meant it came from a translation in this case, okay? So you're basically translating it by the length, the base, yeah, to the right. See that? So like the base A would go to B, right? This point would now go to some point here. It's 9 degrees. Yeah. This point will go to C, yeah? Okay. And I guess none of the points here would go on here, right? It would all... No, so all of these points here would go on here, yeah? Yeah, so then it's exactly this area, okay? And it's a rectangle. At this point, I guess we do know that this is the base, yeah? We either know it from there or that we can look at the translation directly. Yeah? Okay. So if that's understood, then there's an exercise. So the exercise is, if you're given a segment of length A, yeah, and a circle, okay, two fixed things, yeah, can you figure out a way to draw inside the circle a rectangle where one of the lengths is parallel and equal to this segment? That make sense? With side like equal to this as a vector, yeah, basically. Let's say. No, they're saying another name for translation is vector. It just feels grammatically incorrect. Is a vector, yeah. So a vector is translating. I mean, it has its merits.
Oh, no. Oh, that's just,
No. Okay. David is saying you get the center and draw a perpendicular line from there to the segment. Oh, let's explore this stuff. There's a segment right here, yeah? You got the center, you draw a perpendicular line. And then what? And transform it from there.
what?
So you can definitely translate it so that that point is the center. You get like this, yeah. Flip it around. So I'll give you another 10 minutes to do this, okay? Okay, so you can draw the line through the center parallel to A. Okay. Perpendicular. Perpendicular to A. So like this. So that's the one perpendicular, that's the one parallel, yeah? The center of A will be on that line. Center of A will be on that line. What's A?
Yeah, the center of A plan is on the perpendicular.
This one?
Yeah, 4 times.
The center of what?
Of the line when it comes
This one?
the midpoint. Yeah.
This midpoint here?
Yeah, when it's translation.
To here?
No, to the chord.
I'm sorry, I don't understand.
Like, isn't the problem like moving that to like be a chord of the circle?
Yeah, it's equivalent to that, yeah. A chord there.
When you go to chord, the midpoint of the chord, it has to be on the perpendicular.
Yeah, so you're saying
That's what that's.
so this is the midpoint, yeah?
Yeah.
Oh. Oh, so I guess you know how to translate. Okay, so I guess from that you know that you have to translate this thing that way, yeah? If that's your observation, then you can translate that way by. So that's where the midpoint has to be, right?
Yeah.
There. So you put that there, right? So then you get it. Then it's there, right? It's equivalent to it being outside the circle there. Yeah.
Yeah.
So you just translate it by this distance. Yeah.
Move it down. Can you use like prime factors on the like you draw the radius from the center to where the cool touches the circle?
Or you mean find like this length or something,
Yeah.
and then find this length.
Yeah.
Oh, I see. So you have the radius, right? You're finding this. You're finding the length A basically. But do you know the angle?
Maybe.
Oh, you know the length A. You know the length A, yeah. So this is A on 2.
And that one
So then
is r
you,
squared minus b.
so you can find X, right?
Yeah. And then you just move it so the distance, the perpendicular distance from the center to the line minus that amount.
Yeah.
Yeah.
Okay. That's pretty good.
Is that how you want to do it?
Oh, there's obviously an elegant way using translations. I mean, this is the translations section.
This is the backsheet.
Yeah, I mean, this is sort of, when you're forced into a corner, bash.
Yes.
But yeah, so this is sort of the coordinate translation, yeah? You can even, I guess you can do a translation without coordinates. Yeah. Okay, so I guess it's time to talk about the solution then. People solved it somehow. Okay, so you can do a translation without coordinates, yeah? You see? So you take a circle, okay, and you have a vector A, right? You can translate the circle by A.
Oh.
Yeah? You translate the circle by A, yeah? The point of intersection and its pre-image. You know what I'm saying? So let's look for a coordinateless way. Okay? So you translate, but then you might wonder like how you actually carry out the translation. So you might introduce coordinates later. So translation of entire circle by AB, yeah? Okay.
Oh, what if the circle is going to intersect?
Well,
No, they will, because
yeah.
Oh yeah.
So actually, this is something you could. This is actually something you could have thought of before, right? But this really forces you to think of it now, right?
Yes.
Because the A might not have even fit into the circle before, right? So the A has to be such that it's at least it's at most the diameter, right?
Yeah.
If A is bigger than the diameter is, you can't do it,
Yeah.
and that's when it doesn't intersect,
Yeah.
right? And if it is equal to diameter, then it just touches, right?
Yeah, and that's
And it's still a point of intersection.
Yeah.
Okay? So now you're looking at basically, like, let's call this point C, right? C prime. And then you can undo, the translation's invertible, right? So you just have to translate by negative A, then you know it has to be C, yeah?
Yeah.
Yeah? So that has to have length A,
yeah.
Oh.
right? I don't think the book really explains it. It just draws a picture. But
Yeah.
see, you take the point of intersection, and then you don't have to even translate it again. You can just use the other point of intersection, right?
Yeah.
Isn't that cool? It's pretty elegant, yeah. So the points of intersection give you where you need to put the ends of your interval. Okay. So how would you like? So it might be easy to say translate the circle, but you might get worried about how to actually carry that out, right?
Just take every point on the circle.
Yeah. So the thing is, a lot of the time, so I was like, whenever something like that crosses your mind, okay, in my experience, that's always been like an issue, and it needs to be actually solved and has an answer most of the time as well. Yeah, it's never like, oh, that's nothing, or it's like, oh, that's not like part of the question. It's always part of the question somehow, right? So I don't know. One way you can think about it maybe is like how do you even translate stuff? If you think of them in coordinates, right? Like you can put the segment A onto the origin, right, and measure the angle, for example, and then you can figure out sort of the coordinates of the segment, yeah,
Mm-hmm.
yeah, and then so now if you have coordinates of these points, like maybe A could be like AB, yeah, and this is like X Y, yeah, and the translated is just to add Y plus B, yeah. So that gives you an explicit way to carry out the translation if you really wanted to. Maybe that's why it's called a vector, because you're actually adding, you know. The vectors need to be added. And then I guess figuring out the coordinates from this angle is trigonometry. Maybe that's what we'll get into next. So we need to lengthen the direction. Yeah. And obviously, you know, the only way to have a thing inside the circle is to have a rectangle, you know? So you don't have to worry about the other two sides. The only cyclic parallelogram is a rectangle. Because the opposite angles are equal, but they're also supplementary, right? So you don't have to worry about the other case. Yeah, so so the companion exercise, so you, in the email I sent, you can do 4.1.1 and 4.1.2. There's two exercises in this section, yeah. So you can do that on Tuesday if you want, or whenever you feel like. Okay. Yeah, I feel like the book's given us a lot of good moments.